lowercase letters, say A, B, C. And of course the members should be enclosed in these braces here. It should be enclosed in the braces. In the event that we have not listed all of the elements in a set, then we will put these 3 dots or dash dash dash. Some people will say dot dot, but I can say dash dash dash. So if you say A is equal to A, B, C, D dash dash dash, it means that this is, I have not listed all of the elements in this set. But every time you say this is the A, which is simply equal to A, B, C, and D. Here I know the number of, I know the elements in this set, all of the elements. This is A, B, C, D. Of course here you can complete the elements in this set following a pattern. If you say, okay, since someone wrote A, B, C, D, then the other elements in the set should be E, F, G, H up to Z. So you can always look at a pattern and relate what someone wanted to list in a given set. So this set here has the other elements. This one here, the elements are only 4 and they are A, B, C, and D. Of course, we are saying that they should be enclosed in these braces here. So when you want to say that something is a member of, then we will use this. This means is in or is a member of. For instance, if you say a set A is equal to 1, 2, 3, and 5, then I can say that 1 is a member of A, or 1 is in A. 2 is in A. 3 is in A. Of course, 5 is also in A. But 4 is not in A. So this one here means is not a member of A. Is not a member of A. I hope that is okay. So the sets, the set of English vowels, this one here is a set. Members of a family, Opolot, Adong, Abuti, and so on. And let's look at the best concepts. Please feel free to ask at any point. Feel free to so probably you can raise your hand or you can unmute and ask for clarification the event you need it. So we have some concepts, or the basic concepts in a set. We have what we call symbolism. Symbolism. And here we have 2 ways of representing a set. The first one is the tabular notation, or simply listing elements. And for example, write the set A, which is equal to x, such that x squared minus 3x plus 2 is equal to 0. Okay, problem. Let me just, I want some space here. I want space here. Let me say A is equal to x, such that x squared minus 3x plus 2 is equal to 0 in tabular notation. So when if I am given this, then I have to solve. The set A contains the elements x such that when I square x and subtract 3x and add 2, then I get a 0. So which elements are those ones? What does that mean? That I now have to solve. I solve and say I have x squared minus 3x plus 2 is equal to 0, meaning I have x squared minus x minus 2x plus 2 is equal to 0. Solving this one, we have x into x minus 1 minus 2 into x minus 1 is equal to 0. So you have x minus 2 into x minus 1 is equal to 0. So either, for me to have this, it means for a product of two numbers to be a 0, it simply means that one of the two is 0, or even both. So it is x minus 2 is equal to 0, which implies that x is equal to 2. Or if x minus 1 is equal to 0, then x is equal to 1. So the set A is then 1 and 2. So these are the values of x. So here, this is the listing notation or tabular notation. This is the tabular notation. I have listed elements. One can say A is a set of vowels in the English alphabet. Of course, we have this one here. A set can be represented by listing its members. Such a set is said to be defined. This is called the tabular notation, presented as xy. So this is what we have. Write the following sets in tabular notation. W is equal to even numbers less than 10. So what is W? W is then if even numbers less than 10, that's 0, 2, 4, 6, and 8. Less than 10. A is a set is equal to colors of the Ugandan flag, and that's black, yellow, and red. X is a set of consonants in the English alphabet. Of course, you see why even here you have to go ahead and say a set of consonants in the English alphabet, because we have a number of alphabets. In Uganda, I think I did in Uganda in O level, we had what we call the Walifu Uganda. It's a different alphabet, because in Uganda we don't have X, we don't have Q, but rather we have Nya. We have this Nga for those who know Uganda. And in your respective languages, their letters you don't have, but you'll find them in other. So that's why it is very important that even when I'm saying X is a consonant, I should define in which alphabet. In which alphabet, because we define the set to be a collection of well-defined things, and these things are called the elements or members or well-defined things of, a well-defined collection of things, or the objects or members. So I'm saying that here it is very important. Of course, here the assumption was that we are talking about the English alphabet, but in the Luganda alphabet it will be a different case. In the Acholi alphabet it will be a different one. In the French alphabet it's a different one. in the Greek alphabet, it would mean different elements in here. So the other one you have D, X is the an odd number between 1 and 10. So this is what we have. This is 3, 5, 7, and 9, and so on. But then we also have the set builder notation. We have talked about the tabular notation. The other way of representing a set is the set builder notation. When you talk about a set builder notation, we simply write a set by defining the characteristics of elements in that set. For instance, a general letter like X is then used to represent any arbitrary member in the set. The set in example 2 that we have just written in tabular notation were given in set builder notation. So all of these elements here were written in set builder notation. In set builder notation. Because when you only give one letter, say X, which represents any arbitrary elements in the set. For instance, write the following sets in set builder notation. You have A is A, E, I, O, U. So how do we write this? This is X, such that X is a vowel. And it is important to add, for me I would be happy if someone said X is a vowel in the English alphabet. English alphabet. Because in the Greek alphabet, for instance, alpha is a vowel. When you're talking about the Greek alphabet, you have alpha, you have beta, you have gamma, you have epsilon, you have phi, you have eta, you have xi, and so on. You have sigma, but you also have the lowercase sigma. You have delta, and this is the lowercase delta, and so on, and so on. You have these ones. You have nu. So that's why for me it is nice when someone says X, such that X is a vowel in the English alphabet. It actually it's better well defined this way. When you go ahead and say from which alphabet. Okay, you have B is 1, 2, dash, dash, up to 10. So this is X, such that X is a counting number from 1 to 10. I have my set here. Of course, you have all of these examples here, but I have this set, for instance. I have A, or let me use the X. I have X, which is equal to this is equal to 1, 4, then I can have 9, 16, 25, 36, dash, 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 up to 81. So who can write this set in set builder notation? Yes. You are saying this is X is equal to X,
such that X is a square number.
Is a square number. Thank you. But I want to put a star and hear from someone else.
Can I redefine it?
It's okay.
X is a square number from 1 to 81.
Okay. We're saying the other alternative is x such that x is a square number from 1 to 81. I also want to put a star. Don't worry. Thank you. Can someone give us the yes, Mugisha?
Well, I would like to put it in this way. X such that x is the square of numbers from 1 to 9.
Okay. You are saying that x is equal to x such that
Such that x is the square of number from 1 to 10. From 1 to 9, sorry.
numbers from 1 to 10.
1 to 9, 1 to 9.
Okay, 1 to 9. Okay. Thank you. Any other alternatives? Thank you, Timothy, and the other one I think was Stacy. I don't.
Yes.
Okay, thank you. Okay, we can all agree that this one here, if we set x such that x is a square number, then it will have more elements than this one here. So we agree that this one is out.
Yes,
But
we agree about it.
still, when we said that x such that x is a square number from 1 to 81, that is okay. I can say that is somehow okay, but not so convincing much as I will cross one eye and say, okay, that's okay. And this one here, Timothy says this is x such that x is a square of numbers from 1 to 9. Now, instead of writing these many words, Timothy, you would say x such that this is x is equal to x squared, such that 1 is less or equal to x and is less or equal to 1 to 9, and x is a counting number. All such and x is a natural number. Of course, I will tell you what, when we talk about natural numbers, we mean numbers 1, 2, 3, 4, and so on. So here you will say you have this set of natural numbers here. So I am picking x. But remember, when you square a negative number, for instance, if I square -1, you get a 1. If I square -2, this is equal to 4 and this is equal to 2 squared, right? So, to me, the most convincing answer is that x is equal to x squared, such that -1 is less. In fact, this is -10. Let me say -10 is less than x and is less or equal to, or I can say is less than. I'm going to give you another alternative. -10 is less than x, x is less than 10, and x is an integer. And x is an integer. Of course, you know integers are whole numbers. And later we will talk about these special sets of numbers, where we will say a set of integer has -2 dash 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 negative 2, negative 1, 0, 1, 2, 3. You get it? But when you look at this definition I have given here, of course, choosing the integer here, you will start from negative 9, negative 8, blah blah blah. But when I say x is an integer, then I have included a 0 in this. I don't know whether you notice that. So we need to be very careful. Then I am including a 0 in this set, meaning it will have 0, 1, 4 and all of that. So here you even have to go further and say except 0 is let me write it precisely using symbols. And x is an integer but minus 0. Equal to 9. Is that okay? Of course, from this one, and x is an integer, of course, minus a 0. You see, here you have written, this is okay, somehow, but I mean, even this one, Timothy. Is that okay? But now we want to look at a broader. I know this x contains square numbers, the set x contains square numbers. But still, where did I choose those numbers that I squared? From which set did I choose the square numbers? I have defined everything. It's fully defined. I don't know whether Timothy you notice the difference between my answer and your answer. They are both okay, but one is a bit advanced, and that's what we want. That's why we are looking at sets here at this level. But we want to understand more things. Okay.
Recording in progress.
We have the tabular notation. And here we say we list all elements, and we have the set builder notation. And what did we say here? Here we said we list an arbitrary element, x, and this is such that sometimes we use full columns, sometimes you can draw this line here, they all mean the same, they both mean the same thing, so we can use them interchangeably. X such that then give the characteristics of elements. Of elements in the set. So that's for set builder notation. Now we have other things. We have the cardinality of a set. The cardinality of a set is represented by this to mean the number of elements in a set. So when you have this set A, which is ABC, its cardinality is equal to 3. It has 3 elements. This one has cardinality 3, but this one here also has cardinality 3. Because when we are writing a set, we always have to avoid repetitions. Because for you, for computer science, you know that when you write negative, you are not optimizing memory, you are using a lot of memory. So in some way it affects the efficiency of a computer. So you avoid this redundancy. So when here C is actually equal to 1, 0, negative 1. This is C here. So its cardinality is 3. Why are we saying it is 3? Because we don't want repetition. And we are saying that the cardinality of this D here is 1. So you have examples that you can look at, but we have subsets, equality and equivalence of sets. Someone is writing. After you are writing in my screen, kindly erase that. I cannot erase it on my side. Please erase that. So we have subsets and given A and B, two sets A and B, a collection of set A that are also members of set B is called a subset of A. And we normally write A is a subset of B, meaning that all members in A are also in B. So we write this to mean A is a subset of B. In this case, we also have a possibility of two sets being equal. In this case, we have a possibility of these two sets being equal. So this one, A is an improper subset of B, because there is a possibility that A is equal to B. But in most cases, even when we are talking about a proper subset, then we will have A is, because this, for instance, when you have, let me give you some example different from this. When you have 2 is less than 4, is this true? Is this statement here true? 2 is less than 4. Is that true? Yes, this is true. But I also have 2 is less or equal to 4. How true is this one here?
You square 2 you get 4.
No, don't look at squaring them. Now, look at them in a sense of comparison. You're trying to compare. We are saying it is true that 2 is less than 4. But is it true that 2 is less or equal to 4? Yes, Mugisha.
Well, there are two conditions. So, 2, the less than satisfies it, but equal to that is so it's not true. Oh.
No, but you have 2 conditions are
equal to. We will look at that later. We shall have to look at that later in propositional logic. But when you have all, if one of the
conditions is true, then the statement is true. So this is true because 2, indeed 2 is less than 4. Much as it is not equal to 4. So this one here is true. Is that okay? Because we are saying less or equal. So you have something, you have all. And for all, once one of the conditions is true, then the statement is true. Is that okay, Mugisha? Does it make sense now?
Yes, it does.
Okay. And we have some definition here. If the set A is a subset of the set B and A is not equal to B, then A is said to be a proper subset. A proper subset. If the set A is a subset of B and A is not equal to B, then A is a proper subset. In the event that A, and actually it is written like,
in the event that A is equal to B, then A is an improper subset.
we have examples of the subsets. The empty set is always denoted by this, all this one here, is always a subset, is a trivial subset of any given set B. So when you're asked to give subsets of a given set, this is the empty set is always a trivial subset. Is that okay? So here we have A is equal to 1, 2, 3. Sets that are made from singletons of this one here, of the elements in a set A, will always be subsets. For instance, C is equal to 1, of course they forgot the braces here. D is equal to 2, E is equal to 3, F is equal to 4, and this one here. These are all subsets. I think this was some kind of repetition because this was just an element. So these are all subsets of B, of a set A. And if you pair these elements 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, these are all subsets. Then when you consider the triplets, the three elements 1, 2, 3, 1, 2, 4, 2, 3, 4, these are all subsets and the state itself. All of these ones here are the proper subsets, are all proper subsets of A. And the Q is an improper subset. This Q here is an improper subset because it's the set itself. And how we write this is this one here, because they are actually equal. Now, the possible subsets are 16, and actually that, okay, probably we'll talk about that later. But if a set A, if the cardinality of the set A is equal to n, then the number of all subsets of A, or the cardinality of all, the number of all subsets of A is given by 2 to the power n. This is the number of all subsets of a set A with any elements. So the number of all the subsets of these ones here will be 2 to the power 4, which is equal to 16. If you counted them, you have the empty set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There is something missing. 2, 3, 4. Let me see, this is the 1. This is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There is something missing here. There should be 16 of them. 1, 2, 3. 1, 2, 4, 2, 3, 4. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. Then 3, 4. Then the set 1. That one over 2, that one over 3, that one over 4. And then the empty set. So these are, if you don't know, I should do it. Oh, yes, it's in Roma. It's in Roma, you have something to say.
Good afternoon. I was asking if you counted the empty set as well.
The empty, yes, I was counting because this is 1. This is the empty set. Then 2, 3, 4, 5. Yes, it's Roma. These are 5.
You're missing on the triplets. I think 1, 3, 4, because I think the numbers are so 3 times. Yeah, 3 times.
Yeah, sure. Okay, thank you.
1, 3, 4.
Yeah, good.
We have the
We have the 1, 2, 3, 4. Thank you. So those are the 16 elements. Of course, when you have more elements, then you're coming up with all of the subsets. For instance, if you have the 5 elements in the set, then it will mean that you will have 32 of them. And so coming up with all of these subsets will be a bit problematic. For a simple set, for instance, if you had the, let's say you had the set A with A, B, and then C, then actually I think before we talk about this, let's even talk about what we call the power set. The power set of a set A is denoted by P of A, and this is the set of all subsets. Is that okay? Is the set of all subsets of the set A. And the cardinality of this power set of A is given by 2 to the power the cardinality of A. All subsets. But when you're talking about all proper subsets, then you will subtract 1. Why? Because the set A is not a proper subset of itself. So if you have this, the subsets will be, the power set of A is going to be given by A, B, C, then AB, you have SC, then you have BC, then you have ABC, and you have the empty set. So 1, 2, 3, 4, 5, 6, 7, 8. So the cardinality of P is indeed 2 to the power 3. P of A is 2 to the power 3, which is equal to 8. All of the subsets, including the improper subset. So all of these ones are the subsets of the set A. And you can see you have 1, you have 2, you have 3, you have 1, 2, 1, 3, 2, 3. The empty set and the set itself. Now, 2 sets, of course I talked about the power set. What happens if someone told me, if someone gave you a set A, which is equal to 1, then 1, 2, and then X, and then they tell you to find a P of A, the power set of A. So we have this. Take that. So I have my P of, I mean A is equal to 1, 2, and the X. So what is the P of A? Remember now A, what you look at here, or what you notice here is that A is a set of sets. It is a set of sets. So the power set of A will be a set of sets. Okay, someone should tell me, can someone tell me this subsets of a set A? Can someone try? We want to come up with the power set of A. Okay, probably let me do it myself, and so this is going to be 1. Is that okay? Then you have 1, 2. Then we have X, the set of set X. What else do we have? We have 1, 2. Then we have 1, and then X. Then we have 1, 2. Then X. What else we have? We have the set A itself, and we have the empty set of this set here. Does that make sense? Because the elements in set A are sets.
Yes,
So when you're coming up with the subsets of set A, it will be set of sets because the elements in A are sets. Okay. Yes, someone is I can see it is docile. Yes, I don't know whether
Good afternoon, sir.
Yes, good afternoon.
I have a question. You said that those subsets are set in A. I was thinking maybe we should first find the power of those sets inside A, then add them together. Like the set of 1 will have its own empty set, set of 1 and 2 will have its own power of sets, then we will add them together for set of A.
Not really, because A is a set of sets. The elements in A are sets. So when I'm choosing the subsets of set A, there will be set of sets. That's why I have a set of sets. These are set of sets. These are sets, but of sets. For instance, I have a set, but of set with the element 1. It will be an element because the power set is a set of all subsets. Yes. A power set of set A is a set of all subsets of set A. For instance, when you're looking at this, 1 is a member of set A. You get if you look at this set A, the set with this element 1 is a member, not actually a subset. So, if I understood your question, you were asking what we have to come up with the. Of course, because these are sets in A, we first come up with all the subsets of each of the set. Of course, we would have, then it would even define whatever the theory that the cardinality of the power set is 2 to power the cardinality of the set A, or 2 to power A. Because if I am to come up with the power set of this set 1, then it would have 1 and the empty set. The power set of this set here would have 3 elements. It wouldn't make any sense. I would just make life hard. But when you're looking at this set, it is a set of sets. The elements in the set, actually, just like when you're talking about the power set, the elements in the power set are the sets. The elements in a power set are the sets. I don't know whether I have answered your question.
I want to hear from you.
Have I answered your question? Does this? Yes?
A little bit, because at the beginning you said that sets has to be in a bracket, so those ones inside are not just elements of A because they have bracket, that means they are set of its own.
Yeah, but here the elements in set A are the states. So if I wanted to write it that this is a subset, then I would have to enclose it in other braces. Then that's how I can manage to say from the limit simply this. Yeah. How I can write that this is if I want to write a subset containing this, then this is the subset of A. This one. Because a set A is containing sets, the elements in the set A are the sets. So much as these are sets, but they are simply members in the set. If you're writing the subsets, then you have to choose these members and enclose them in braces. So here I have given a set A with the n element. What is the cardinality of the what's the set
I have a set with
T of A.
Recording in progress.
set of the power set of the knowledge makes sense. But I will the cardinality of the power set of the power set of the. So what is that? Yes, Timothy?
Well, I started by asking how are we referring to the earlier statement of the air, which is one.
Yeah, sure.
So
No, we are not. Now, this is a general one. You have
General one.
a set with the any elements.
okay.
You don't know any, just with any element.
All right. So my assumption is so. All right. So since A we have seen that the cardinality of A is A, right? Cardinality of the power of set A is to the number of A, right? In that the power set to the power set will be the cardinality of the area power set.
This is the 2 to power.
Okay.
That one. Is it what I have written? Okay. Thank you. That's it. That's it. In fact, let me take you. If I wanted to write the power set of the power set of this one,
Recording in progress.
then it would simply be 2 to the
B2
power 8.
to the power 8.
Simply B2
To simply B2 to the power 8.
Thank you, Timothy.
Thank you, Timothy. Of course, we have looked at the subsets, and of course, I have used that to explain the concept of a power set. We can now look at the equality of sets, and sets A and B are said to be equal if A is a subset of B and B is a subset of A. Meaning that all elements in A are also in B, and all elements in B are also in A. So those two sets will then be equal. So for two sets A and B to be equal, these two conditions should be satisfied. And the two sets are equivalent if they have the same cardinality. Two sets are equivalent if they have the same cardinality. Of course, you have some examples here. A is equal to AB and B is equal to AB. So A is equal to B here. The same thing here, A is equal to B. Same thing here, A is equal to B. Because all elements in A are also in B and all elements in B are also in A. And I'm saying that two sets are equivalent if they have the same cardinality. And how do we write equivalence of sets? It is A is equivalent to B if the cardinality of A is equal to the cardinality of B. That's when we can conclude that two sets are equal if they have the same number of elements. So you have this one here, R is equal to 2468, S is equal to 246810. So these two sets are not equivalent. R is not equivalent to S. Why? Because since the cardinality of R is equal to 4 and the cardinality of S is equal to 5. So they are not equal. They are not equivalent because 4 is not equal to 5. So we have types of sets. We have the universal set. A universal set is normally denoted by U, S, or eta. This is a Greek, just a Greek letter. Yes, someone is Peter. Yes, Peter.
Okay. that
Yes?
you're saying that two sets can be equivalent in case they have the same cardinality, but what if the two sets do not have the same characteristics? For example, set A contains vowel letters, vowel letters, which is the first 5 vowel letters in English,
Yes.
whereas the other set contains values from 1 to 5. Do they still remain equivalent?
Yeah. Because the only condition is that we need them to have the same cardinality.
Okay, thank you.
Yeah. Thank you. These are equal, so implying that A is equivalent to B, because the only requirement for equivalence is having equal cardinality. So is a set which has elements of all of the related sets. The universal set is a set that has elements of all the related sets without any repetition of elements. Of course, we have here A, we have B and C. So we have a universal set here, which is a combination of all of these ones. You have 2, 4, 6, 1, 3, 7, 9, 11. So you have these ones. So you can have U, which is equal to 1, 2, 3. I think I have that and that. 4. That goes, no repetitions. Then we have 60, then we have 70, this is 70, 80, 90, and 11. So this is the universal set. But the universal set can have more elements actually. If I wrote another set S and give it elements 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. This also qualifies to be a universal set, because the only requirement is that it should contain all of the elements or objects of the other sets, including its own elements. That's now this one brings in what I am doing here. This other second example, including its own elements, and it is denoted by the symbol eta. Okay. So we have the empty set, and that is the null or void set. It is denoted by this one, pi, or simply the empty braces. You open it and you close. Of course, if you write a set here and say this is 1, 2, 3, dash dash, this one is not a set. Why? Because you have not closed. You have to close. Whenever you open, then you close. We have the power set. I think I have earlier explained this. And, yep. We have the finite set. The set is finite if it has a finite number of elements. For instance, if you talk about set A, which is 1, 2, dash, 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 100, or let me say 100. This is finite. It has 100 elements. But of course, if I talk about an infinite set, has an infinite number of elements. Let me write a simple set A and say this is X, such that 1 is less than X and is less than 2. Do you think that set is finite? Now I believe most of you did mathematics at A level. Most of you. If you have not done with math at A level, then you've done some, what do you call it? Is that compulsory mathematics at A level? Is it the subsidiary mathematics? Submath, subsidiary math. So someone should do. Can someone help me list the elements here? In set A, or probably let me call it X.
Okay.
Yes?
I think the values for x shall begin from 1 to negative infinity.
Sure. You have tried, but you see, x is not even in this set, because 1 is less than x, and is actually less than 2.
So can I try?
Yes, yes.
1 and 2. Actually,
But it is not par, because 1 is less than x, and x is
0.
less than 2.
They are not members because less than you don't include 1, don't include 2. X is just
Now, you see what you're saying, that they are no members. It depends on which set, from which set you're choosing the elements. If I were choosing from integers, then no members. And actually, that's why you gave me correct answers when we were doing the other example, square numbers. But I tried to give you mine that was defining, because in the sense that one is talking about integers, then this will be an empty set. If x is an integer, then it is an empty set. You get? But if it is a real number, then it is not an empty set. I don't know whether it does make sense.
then what
Yes,
number?
it makes sense.
Let's say, let me write two of them. Let me redefine. I'm saying if I say x is 1 less than is x such that 1 is less than x and less than 2, let me say and x is an integer. Then x is equal to empty. You get?
Yes.
But the moment I say that x is equal to x, such that 1 is less than x and is less than 2, and x is a real number, then x has infinitely many elements. I cannot actually, I don't know, I cannot even list them. Because what will be the first element in the set?
1.000. I understand.
You get?
Yeah.
Because 1 is less, then you would say I can have 1.0001. But remember, even when I say 1.0001, there is a 1.00001. So choosing the first element here is even impossible. So this set would be a very huge one, an infinite one. You can't exhaust all of the elements in this set. They are infinitely many. And what would be the last element? You would say, let's write 1.99999, but I can write very many nines here, a million of them. And there is even a number greater than a million. So you can write 1 billion nines, a billion nines. It will be different. So if it is real numbers, this set is infinite. It is infinite because the elements in this set are uncountable. But I'm saying if this is an integer, then this is an empty set, so it is a finite set. Why? Because the cardinality of x would simply be 0. Are we together?
Yes, we are.
So examples of finite sets, you have that. Here you have a such that a is an integer. 1 is less than. So can someone tell me the first element here? 1 is less than a and a is less than 10. 2, 3, 4, 5, 6, 7, 8. 9 is 10 in this set?
No.
No. Okay, thank you. A set of all English alphabets is countable. It has 26 elements and so on. Okay, we have disjoint sets. I think we have other definitions here. When we talk about an infinite set, a set whose elements are not countable. You cannot count. For instance, when you talk about a set of even numbers, is infinite. A set of integers is infinite. A set of odd numbers is infinite. You cannot count all of them. You cannot exhaust all of the elements in that set. So okay, so I think we have the difference between an infinite set and a finite one. We have a disjoint set. A disjoint set, two sets A and B are disjoint if they don't have elements in a common. The intersection is empty. So when you talk about a set A, which is 1, 2, 3, 4, and the set B, which is 5, which is 5, 6, 7, 8. Let me give a universal set to you, and if I give a universal set, which is 1, 2, 3, 4, up to 10. So here, if you try to draw a Venn diagram and try to find elements in common, this is, you have a disjoint set. You have A, which is 1, 2, 3, 4. You have 5, 6, 7, 8. And of course you have 1, 2, 3, 4, 5, 6, 7, 8. You have 9 and 10. So you have this, they don't have the A intersection B is empty. No elements in common. Now you have something about disjoint sets. Of course, this can come out after we have looked at the set operations, and probably let me take you here. I have my Venn diagram here. Set operation. Sets. And of course we have the union of sets. We have intersection. We have set differences. So you have a Venn diagram here. I have This is the A, this is the B. This one here is the universal set. Now here, this is the A intersection B complement. This is the A intersection B, and this is A complement intersection B. Of course, we also have set complements here. And here, this is the A complement intersection B complement. Neither in A nor in B. So when I talk about set complements, let me say A complement. And A complement is simply equal to X such that X is not in A, but X is in the universal set. X is in the universal set, but not in A. That is a set complement. For instance, if I have A which is equal to 1, 2, 3, and I have the universal set which is 1, 2, 3, 4, 5, and then 6. If I need to give a complement, this is simply equal to 4, 5, 6. In the universal set, but not in the complement. Then we have A intersection B, the intersection A intersection B. This is X such that X is in A and X is in B. For instance, if you then what is the A intersection B? What is the A intersection B? Can someone tell me what is the intersection B? It is 1 and 3, thank you. What is the okay, no problem. What is the B minus A? Of course, here I'm now talking about to set differences. What is B minus A? What is B minus A?
B minus A is 2 and 4.
B minus A, no. Okay, I think let me not confuse you. Let me first leave it at that. It's okay.
B minus A is
okay, let's first leave it at that. Let's talk about the set, the union of sets. Union of sets, that's A union B, and the A union B is simply equal to X such that X is in A, all X is in B. X is in A, all X is in B. E.g., I have A, which is 1, 2, 3, 4, and B is equal to X, such that X is an odd number less than 10. So what is A union B? What is A union B?
A union B is 1, 2, 3, 4, 5, 7, 9.
Thank you. That's A union B. Okay. Then, if we talk about set differences, that's A minus B, or simply A minus B, or A intersection B complement. So this one, A intersection B complement, is the A minus B. And this one here is X, such that X is in A and X is not in B. X is in A and X is not in B. For instance, e.g., we have A which is equal to 1, 2, 3, 4, and B is equal to X, such that X is an odd number than 10. So we want to find A minus B. They are in A but not in B. That's what this means. A minus B. These are elements in A but not in B.
I think that is forward.
This is it. Thank you. And what is B minus A?
That is a 5, 7, and a 9.
5, 7,
5, 7, 9.
9. Thank you. So now I should briefly take you to this very diagram here that we were drawing earlier. And here, if you have this intersection B complement, this is A complement, intersection B complement, but at the same time this is A. Of course, we have what we call De Morgan's laws. These ones are A intersection B complement is equal to A complement union B complement. And A union B complement, this is A complement intersection B complement, neither in A nor in B. So this is what we have. These are De Morgan's laws. But we said A and B are disjoint if A intersection B is equal to the empty set. But you see, when you have A union B, A union B is given by A. Is that okay? Intersection B complement union A intersection B union A complement intersection B. Now I want you to consider that here when we're talking about union, it simply means a plus. In terms of when we're talking about the number of elements, the union will always mean plus. So when you have A union B, this is equal to A intersection B complement. And actually, in fact, now let me change to when we are talking about the cardinality. Let me say N of A, N of B. This is N of A intersection B. This is N of that. And this is N of that. Of course, this is N of this one here. So, when we want to find N of A, when is our next lecture? So when we want, this is of course the universal set, N of the universal. So N of A is equal to N of A intersection B complement plus N of A intersection B. I hope you can see that. For me to find this, I get this plus that. And what is N of B? It is N of A complement intersection B, this one here, plus N of A intersection B. What is the N of A union B? N of A union B is equal to N of A plus N of B minus N of A intersection B. Can we prove this? Can we prove that indeed N of A union B is equal to N of A plus N of B minus N of A intersection B? Because if we want to find the N of A union B, then this is going to be this one here, N of A plus, but remember you do not want to have repetitions. That's why you're subtracting this N of the intersection, because if you are having the N of A plus N of B, remember N of A has the intersection, then N of B also has the intersection. So this one here, N of A union B is equal to, how should I write that? Let me say it is this one. This first one, N of A intersection B complement plus N of A intersection B, then plus N of A complement intersection B. If I am finding the union, I will add this to that. But what is the N of A intersection B complement from these equations, from these ones? This is equal to, when you make N of A intersection B complement the subject, to be N of A minus N of A intersection B plus N of A intersection B plus make N of A complement intersection B the subject. It will be N of B minus N of A intersection B. Of course that goes with that, and what are you left with? It is N of A plus N of B minus this N of A intersection B. When you want the whatever the complement, it will be the n of, the universal set will be n of A union B plus n of A complement intersection B complement. So this Venn diagram here and these derivations here will be very, very important. So you have some of them here, and even when we're talking about the three whatever Venn diagram, and that's why the one of the disjoint, when you're talking that if A and B are disjoint sets, then n of A union B is equal to n of A plus n of B. Why? Because we would subtract this, but the number of, since they are disjoint, n of A intersection B is 0. So that's why we simply have that if we are talking about the disjoint sets. N of A union B is simply equal to n of A plus n of B. So these are set operations. We have looked at them. We have looked at the differences. And you have a number of examples. We talked about the complements. Venn diagram, I have talked about the Venn diagram. Here you're shading A. Here you're shading B. Here this is the intersection. This is only A minus B. This is only B without A. This is the union, but the complement of the union. Here you have the universal set. You have the union of A and B, and so on. Of course, you can have the three Venn diagram sets from the adjoining Venn diagram. We find the following sets. So you can use the Venn diagram to look at a number of things. For instance, if you looked at this one here, where you have three sets, let's say you have this and that. So this is a set A, B, and C. This one here is A intersection B complement, intersection C complement. This one here is the A intersection B intersection C complement. This is A intersection B intersection C. This is A complement intersection B intersection C complement. This is A intersection B complement intersection C. This one here is A complement intersection B intersection C. This one here is A complement intersection B complement intersection C. And this is A complement intersection B complement intersection C complement. So here you're talking about this. So when you're talking about A intersection B intersection C complement, these are elements that are in both the A and the B, but not in C. So you can have a number of examples here. For instance, here, if you wanted the A intersection B complement, intersection C complement, this is a 3. What is the A intersection B intersection C complement? What is the A intersection B intersection C complement? Both in the A and the B, but not in the C. Step 4. What is the A intersection B intersection C?
What is infinite?
Now, that's the universal set. You have the C minus A and that. you have these ones here, and of course we have examples from the Venn diagram. We have n, probably let me treat my screen. So this is the paint. Paste. Of an example. Yum. Copy. This should be our last example. Given that the number of the elements in the universal set is 18, the one in set A are 7, we can use a Venn diagram. So we have n of A is 7, n of B is 8, n of the universal is 18, n of A intersection B complement is 4. So we can find the rest. One, we can find n of A intersection B. We can find n of A complement intersection B. The complement can be written as prime or A, C. And we can find n of A complement intersection B complement. We can find n of A union B. So if we let this be x, then what does that mean? That this one will be 8 minus x, and this is 7 minus x. So what does that mean? N of A intersection B is equal to n of A minus n of A intersection B complement. So this is the x, and this one here is equal to
7.
7 of course minus x, but this one here is equal to 4. I hope that you can see that. Let me rewrite this. We have n of A is equal to n of A intersection B complement plus n of A intersection B. And we said this is x. So n of A is 7. This one here is a 4. And this one here plus x. And so x is equal to 7 minus 4, which is equal to 3. So this one here is equal to 3. Are we together? And what is n of A complement intersection B? N of B is equal to n of A complement intersection B plus n of A intersection B. We have the intersection, we know n of B, so n of A complement intersection B is equal to 8 minus 3, which is equal to 5. So this is a 5, that's a 3. What is n of A union B? We said this is n of A plus n of B minus n of A intersection B, which is 7 plus 8 minus 3, and this one here is a 12. Of the universal is equal to n of A union B plus n of A complement intersection B complement. We know this one here is 18 is equal to 12 plus n of A complement intersection B complement. And what does that mean? That A complement intersection B complement is equal to 18 minus 12, which is equal to 6. Is that okay? That is equal to 6. So you have all of these ones here. And you have very many examples. Please go through these examples. The teacher always does one example, and the rest is left for students to try. So please, during this time when you stay home, kindly do your best. Try all of these examples. Next time we meet, we should be in a position to complete sets and look at another chapter, probably permutations and combinations, or because normally in the 4th week we have to do tests. So find a way and try your best. Otherwise, I want to thank you for your time and for responding, because it was on a short notice. I want to thank you for your time and wish you the best. My contact is 0702 64 70 67. That's the WhatsApp contact. Feel free to contact me whenever you're stuck, at any time of the day. I don't have restrictions. Just feel free to contact me whenever you're stuck. I will be available to help and give guidance accordingly. Otherwise, I want to wish you a blessed week and thank you for your time. Have a good evening.